Then, with some reminiscences which I thought were interesting, let us examine the fact that Raman, uh, before doing the Raman scattering as such, he had a knack of optical physics or physics of optics or something, and he was uh, doing and he was attracted by the blue of the sky. So blue of the sky, why the sky color is blue, was something which he did for the first time, which he noticed while he was traveling to England. And while he was traveling to England, he could see this thing, blue of the sky. And अभी हमारा क्लास चल रहा है, थोड़ी देर में बात करते हैं आपसे, थोड़ी देर में. By that time, the very famous physicist it was believed that the blue of the sky is blue of the sky is due to reflection of blue of the sky was due to reflection of light, reflection of uh, light, and because the sky is blue, the sea was also blue. And why the sky is blue and sea is blue was thought to be fact that somehow the sky was blue and reflection of that in the water gives a blue color. Raman, while traveling to England later on by a ship for attending a conference, he always carried a small spectroscope in his pocket and some nickel prism. So he tried to verify whether this is true, that whether the sky is blue and therefore the sea is blue. And he used a small spectrometer which was having in his pocket and filters and nickel prism, and he found that even when the light was cut off, it looked like blue. So therefore, even when the light is cut off from the coming from the sky, even then the sea was blue. So he said that some of the hypotheses put by Lord Rayleigh and others that the sky is blue is not correct, and it may be due to some other reason. And then he was able to say that this blue has a lower wavelength, and therefore say 490 to 450 nanometer, and therefore it will undergo huge scattering. Small wavelength, small wavelength means high energy. So blue light has a high energy. Therefore, it went.
వీడు రోడ్డు మీద అన్ని గతుకులు ఉండే కదా మెల్లగానే వచ్చింది మెల్లగానే వచ్చినా కానీ
Yes. So sorry, the blue. So he explained that because of the fact that the wavelength is small, the energy is high. The scattering therefore is not inversely proportional to wavelength. The smaller wavelength means higher scattering, and therefore it is because of the scattering from the particles. So there's several types of aerosol particles that the sky looks blue, and not due to the fact which was thought earlier. So you see, he has a great knack of recognizing the things, and this paper was published. And then why the sun is red in the morning? Because the red has a larger wavelength. So this light comes much faster and it reaches the earth. Therefore, right in the beginning, the sun looks like red, but slowly and slowly this disappears. So these things he was able to explain like this. Then entry of Raman into research. The building, the Bau Bazar Street, Calcutta, where this ISCS was located. This is shown here. This building was the place where Raman started doing his research, and here he was offered that place and a small amount of funding for carrying out the research in ISCS Calcutta. And this is the spectrograph. This is the initial spectrograph which he was able to assemble. And as you can see, this is all looks like coming from the Kabadi Bazaar type of thing. And and the and assembled there, Raman spectrograph. The first Raman spectrum was recorded with this spectrograph in 1928. So you see, with such a locally made spectrograph, the locally assembled spectrograph, Raman was able to uh, do this, uh, discover this effect of Raman scattering. So this is the initial, this is another reminiscence of about Raman. And the experiment that he carried was simple in the sense that he used several types of liquids, and he has a sunlight. White light was the source of light, and then he has liquid benzene, alcohol, and things like this. And then this high energy light was coming here, and then it was undergoing this thing. So most of this is elastic scattering. So this is Rayleigh scattered light, but some of the scattering was not Rayleigh. In other words, the frequency and wavelength of the scattered light changed. And then he put some filter, and then he observed. So this light, which has the same wavelength as the incident light, the Rayleigh scattering, is very strong. Therefore, you can see it easily. But the other light, which is due to scattering from the interaction of the incoming photons with the molecules of the liquid, and therefore the frequency changes, is very weak. So usually we will not be able to see this thing. So what Raman did is that he made a dark room. He made his room completely dark, and then he kept his eyes closed for half an hour, and then opened the eye. Then he could see a very feeble trace of this Raman scattered light, and that is the way he was able to guess. He was able to first guess and then confirm that there is another component in this of the scattered light which has a wavelength different than the incident wavelength. Therefore, it is different from the usual Rayleigh scattering. And then Raman wrote this paper, and title was A New Type of Secondary Radiation, Nature, London. And this was in 1928. And he was very smart, so he sent this paper by telegram. At that time, this email and fax, etc., were not there. So he sent by telegram, spending his own money because there was no money available at that time. He said the new type of light scattering discovered by naturally requires very powerful illumination. So in our experiments, a beam of sunlight was covered successfully by telescope objective at 10 centimeter aperture and 21 centimeter focal length, and by a second lens of 5 centimeter focal length. At the focus of the second lens was placed the scattering material, which was a liquid, which is either liquid carefully purified by repeated distillation in vacuum, or its dust-free vapor. To detect the presence of modified scattered radiation, the method of complementary light filters was used. A, a blue light, a blue light filter, when coupled with a yellow-green filter and placed in the incident light, completely extinguish the track of the light through the liquid or vapor. The reappearance of the track when the yellow filter is transferred to a place between it and the observer, the proof of the existence of a modified scattered radiation. So this is the Raman scattered, modified scattered radiation, and spectroscopic studies also have confirmed this. So some 60 different common liquids were used. So in the paper which is sent to confirm that it was really true, some 60 different common liquids have been examined in this way, and every one of them showed the effect of greater or less degree. In other words, every one of them showed that there is another component of scattered radiation which has a frequency or the wavelength different than the incident radiation. That the effect is true scattering and not a fluorescence is indicated in the first place by its feebleness in comparison with the ordinary scattering and comparable with the polarization, which in many cases is quite strong and comparable with the polarization of the ordinary scattering. The investigation is naturally much more difficult in the case of gases and vapors owing to the excessive feebleness of the effect. Nevertheless, when the vapor is sufficient density, for example, with ether or aniline, the modified scattering is readily demonstrable. So these three PowerPoints show the total paper of about 1.5 page, which was communicated by Raman. As I told you that this is the paper, say, first page, uh, second page, and then this third page. So he has made it clear that the result is real by using 60 different liquids, and in every liquid, more or less, either feeble or a little bit strong, depending on the molecular nature of the liquid, effect was present. The effect that the scattered light has a different wavelength. So that was the story. Now there is some controversy here that the suggestion was given by uh, I have not written this, but the suggestion that such a thing is going to happen was given by Raman, but the actual experiments were carried out by one his student K.S. Krishnan. And in the citation of Nobel Prize, it is written that the actual experiments were carried out by K.S. Krishnan. But the name of the K.S. Krishnan was not there. He did not share the Nobel Prize. So there is some controversy raised, particularly by German scientists and so on. This is one type of controversy that just like you see Gaim and Novoselov, the graphene people, the idea was given by Professor Gaim. But the actual experiments of exfoliation of graphite by tape was done for several years by Novoselov, his student. So both of them shared the Nobel Prize. But in this case, the Nobel Prize was only given to Raman, possibly because of the fact that Raman was already established scientist. By that time, he was a quite established scientist. He was known abroad, and some of the scientists like Woodward and Rayleigh favored him very much, and therefore it was given singly to him. And this is the diagram. You have this one of the vibration level is here, and here you have transition, radiationless transition, then there is radiation transition. This is the diagram which he attached there. And as you know, there is for example, this is the spectra which they recorded, and this is the feeble line which they were able to see here and here at 4046 and 4358 spectrum, showing that a different the scattered light has a different frequency and wavelength. And this is the diploma in emblem which was given to him, this Nobel Prize. Now, this diagram tries to show what I told you in some detail. For example, you see here that these are the virtual energy states and these are the vibrational energy states. And if there is excitation from here, and it goes up to one of the virtual energy states and returns back to the same from where it is started, then you have no change in the wavelength and you have the Rayleigh scattering. But if the excitation is from this place and then it returns to a different energy level, corresponding to one of the vibrational energy levels, then the frequency of the wavelength will be different. It can be more than this or less than this, depending upon whether it is this type or this type, and therefore this is anti-Stoke line, Stoke line less, and if it is more than this is the Rayleigh scattering, so which is the most dominant. These scatterings are very feeble. These are the Raman peaks, Stokes, anti-Stokes, depending upon whether it is of this type or this type, and Rayleigh is of this type, returning to same level from the initial level. Then this is the spectra of ethanol and methanol. So there are two different liquids. There are two different liquids, but the change in scattering here is visible in both of them. And then for instance here you have a molecule, some molecule here, and this is the incident radiation. So incident radiation goes and gets scattered. So if it gets scattered and has the same wavelength as the incident one, then you have this Rayleigh scattering. But if this incident photon interacts with this molecule, the vibration mode of the molecule, vibration energy of the molecule interacts with this photon, interacts with this, then the radiation which is emitted has a different wavelength, and this is the Raman scattered wavelength. So this is the Rayleigh and this is the Raman, which is shown here. This is the Rayleigh, and the feeble one is this thing. So now, having told you something about this, I because Raman scattering is used nowadays everywhere in biology, in medicine, and in so many other things for detection and for confirmation of the uniformity and then distribution and so on and so forth at the molecular level. It cannot replace X-ray diffraction because X-ray diffraction is a massive scattering where whole material scatters. Here, this is a localized effect, but then you can distinguish a molecule based on the Raman spectra in the sense that specific molecules have specific Raman spectra, just like specific materials have specific X-ray diffraction peaks. Now, Raman scattering, then this is the last portion of my discussion. Raman spectra for carbon nanostructures, particularly the single wall nanotube and graphene, have been very useful, but there have been some certain amount of confusions and certain amount of, initially at least, and Raman spectra is, for example, there is no other technique than Raman scattering through which you can clearly identify that whether you have a graphene, monolayer graphene, a single layer graphene. A single layer graphene has become very important because of the fact that terahertz devices are being fabricated on this. And the second thing is that two layers of graphene, one layer rotated with respect to the second one, has started showing superconductivity. So these twisted graphene layers have started showing superconductivity. And recently MIT has published that 5 layers of graphene rotated by different angles sitting on top of each other between 1 degree and 3 degree. They show superconductor, they become superconductor with a higher transition temperature. Of course, this temperature is between 1 degree and 3 degree, but this is very interesting that graphene layers, and they are single layers. They're not like ABABAB. ABABAB is a 2H, it's a two-layer system, graphitic system. But you have turbostatic graphene, one layer, monolayer, and the second layer is just rotated with respect to the first layer by a small angle like 1 degree, sometimes less than 1 degree. And these start showing superconductivity. So therefore, much more research remains to be done on carbon nanostructures, particularly graphene. So Raman specific characterization of single wall graphite resolution can provide us with much information about the exceptional 1D property of carbon nanomaterials, such as their phonon structure and the electronic structure. And electronic side, this is the basic formula how Raman is produced. And this is the this is single layer graphene, as you already know, and this is the bilayer. Both are very important. This doesn't have any band gap, but bilayer has a band gap. And then it could be multi-layer. And what I was saying is that if this layer is rotated with respect to this layer by a degree or so, then the whole configuration becomes superconductor. This is the newest work going on throughout the world at the moment. The radial bridging mode is the one through which one can identify RBM. Through RBM, one can identify a single wall nanotube as compared to a multi-wall nanotube. And you can also find the diameter of this with this formula. This is the radial bridging mode of the single wall nanotubes, and generally this peak comes at a very say 153, 1589, etc. Lower 1357 say lower wave numbers, and now Raman spectra of graphene, monolayer and few layer versus few layer, monolayer versus few layer. Now what happens is that in graphene you have a G band, you have a D band, and you have two D band. So sometimes people think, sometimes it's written also that 2D is related to D band. D band is due to disorder or defect, and the G band is because of the in-plane vibration and characterizing the graphic nature. But D is due to disorder. Maybe the disorder is edge as well. And 2D, they say, is related to D, but it is not well understood how it is related, and there are some confusions which prevail. So this is the structure of graphene. This is the graphene crystal, as you see, and this is the hexagonal lattice. This is the Brebel lattice. This is the primitive cell, hexagonal cell which can be selected. And then in the reciprocal space, because when you deal with the transitions, then you have to consider the reciprocal space, which gives you the, again, is hexagonal of different magnitude, and this is the direct space. This is the reciprocal space. And the transition, in the graphitic electronic dispersion is formula for G, D, and 2D. So this is G, this is D, and this is 2D. So in the case of 2D, you have a transition with transverse optical phonon. Transverse optical phonon is involved here. Then it comes to these are the Dirac cones. These are the Dirac cones which are well known. And there is a defect here. So this gives one to disorder D. But this defect interacting with ITO, transverse optical vibration, leads to 2D peak formation. For example, it is shown here that if you see, this is the Dirac cone here, and this is your laser light, and this is your graphene. So when the laser light is shown here, then there is a transition from here to here, and then a phonon is emitted, and this phonon makes this transit to the next conical layer. It comes here. Then finally, another phonon, optical phonon comes, and then they combine together and emit this radiation. So the basic process through which it takes place involves a defect and involves a optical in-plane transverse optical phonon, ITO phonon. Let me try to show this again. This is the transition which takes place from here to here. I tried to make this is not given in the book, but then it comes here, and there is another transition, and finally this comes here and joins with this electron, joins with this hole, and there is a emission of a photon. So therefore, the 2D, which is a sort of very important for recognizing that this is monolayer, involving the transition of electrons via in-plane transverse optical phonons, is the one which recognizes this. For example, you see sometimes they write G dash, sometimes they write this G dash peak, but this is actually the most of the time they are writing 2D, and this 2D is due to the transition, the interaction of the electron with the in-plane transverse optical phonon, and this will be, for example, here you see is a 2D band of graphene, which has been monolayer graphene, and this is generally much higher intensity than than the G layer. And one can convolute this to find out whether, with the help of Lorentz transformation, whether this is single monolayer or a single layer or two layer or three layer. So therefore, I think this area, which is carbon nanostructure, is of great importance, and uh, here X-ray diffraction or neutron diffraction, these things, even XPS, are not as helpful as Raman. And Raman is the only thing through which you are able to recognize whether this is a monolar graphene. And MIT people who have been doing this work on superconductivity in graphene have used this technique very prominently. And it looks like that day by day, the use of graphene and new devices and new physics seems to be coming rapidly. First, it was topological insulator found in graphenes, and now it is superconductivity found in graphene. So how many new phenomena graphene is going to show? And if the results reported by MIT group recently, that the number of layer increases, of course, it cannot be many, many layers, because then it will start resembling graphite. But 2 layers, 3 layers, and 5 layers, they said, has resulted in increase of these layers rotated with respect to each other by a very small rotation, 1 degree and 2 degree. Exact, it starts exhibiting superconductivity. So with this, I have this already uh, finished the time duration. And since I said that I wanted to tell a very brief uh, account of some of the reminiscences of Raman, which I tried to show you in the beginning here, that how Raman has a very unusual character. Could not go to England because of the health reasons, became professor without a PhD, and some people supported him so that he gets that professorship. And then, even while being a student of graduate student BA, was able to publish a paper in Nature. And even though he could not do ICS, although he wanted to do it, because for that he has to go to England, he joined this Indian Finance Service, and being serving there in the Indian Finance Service, he got attracted to Indian Association of Cultivation of Science, and then this Mahendralal Sarkar and Ashutosh Mukherjee helped him. So these reminiscences tell a great story, an unusual great story about Chandrasekhara Victor Raman, uh, in whose honor on 28th February we celebrate this Science Day. Yesterday was a holiday, so we are celebrating this, presuming that this is 28th today, or the same day as Raman one. And then thank you very much. Okay, Dr. Kale? Dr. Kale,
Yes, sir.
is it okay?
It's okay, sir. It's very good lecture, and I really thankful to you for even short time you have agreed to give this lecture and this inspiring talk to about the information about the Raman and basic and as well as applications. It was really nice, and then more the study on the graphene, which is the latest thing which people are doing it for twisted graphene and all these things. So it was really inspiring, and actually, it is inspiring us that at this age also you are working. When I have seen you at your place, so you are in the between books and talking to students and all this. I was really impressed and I told my students and other our scientists also, see at the sales also sir is working in this way, and it was really inspiring. And then today lecture was really excellent. Kulkarni ma'am, can you give the
Yeah,
vote of thanks?
yeah. Can you hear me?
Yes, yes, I'm here. I'm able to hear you.
Okay. So I'm given the pleasant task of putting a vote of thanks to you. Uh, Actually, I know Professor Srivastava for many years, and I have also seen him working, and working in a very uh, crowded office, I would say, with a lot of files and books and so on, and also people, students coming in and going out, and he is always busy. Also, he has a knack of knowing the latest things. He keeps in pace with current literature, and many times I have seen that he would put old things and latest knowledge together, and that we have seen today. Today he has given us a very wonderful talk about Raman's memories and how he won the Nobel Prize. Also, very interesting thing he told about Raman's life, personal life also. One thing I should add is that Raman was so confident that he had made this discovery, and he had booked a ticket for going to Sweden in advance before it was declared as the Nobel Prize. So he had so much of confidence that he will win the Nobel Prize, because those days people had to go by ship and it would take time. So he did not want to miss the Nobel Prize ceremony. So that was another thing about Raman. And otherwise, I think Professor O.N. Srivastava has covered almost very important points about Raman, some of the things which I also did not know. He has nicely also expressed about Professor uh, More, whom I know for a long time actually. I was in Pune University Physics Department up to 2009, and till then I knew Professor More. Can you hear me?
Yes, yes, I'm able to hear you.
There is some disturbance, and I'm surprised that he quickly looked at his papers and also told us how important contributions Dr. Professor More has made to science. This is something very remarkable about both of them, that Professor More is contributing a lot, and also how quickly Professor O.N. Srivastava picked up about Professor More. So I would like to congratulate both of them for such a wonderful feast they have given us today on this occasion. And
So,
of course,
Dr. Professor Kulkarni, I am going to send some material to you and Dr. Kale
okay,
very soon, within a week, material called Emzine,
yeah,
which I promised to give to you and to Dr. Kale. So
yeah.
please try to test that material, because we think that this is the correct material that we have made.
Okay. So I would share also that you also have made it, and I will share it with you also. Okay. So
Okay.
we are doing some work. We have made nano composite also of it. So I wanted to share it with you. So we will do that. Okay. So we'll stay in touch, and this is a good occasion that we met. And I would like to thank you for sparing your valuable time from your busy schedule. I know how busy you are, and also Professor More, because he also has come here for the webinar, and I know that it would have been extremely nice if we could all meet uh, personally today, but unfortunately, due to COVID times, we are unable to.
When the COVID is over, we are going to hold a conference here, because
Yes, I will
uh,
be there then.
because our university has been given a what is called University of Eminence (IOE).
Okay, great.
So, and no, not only ourselves, 10 universities, uh,
Uh-huh.
five IITs and five universities like Delhi University and your IIC Bangalore and IIT Bombay, IIT Delhi, IIT Kharagpur. So under that program, there is an exchange program which is open for us. So I
Okay.
will like you, More and Dr. Kale, to come
Yes.
for that conference.
Sure. So thank you very much for the invitation in advance. And I would also like to thank Dr. Kare, who has arranged this meeting today and given us a good chance to see Professor More as well as Professor O.N. Srivastav and have a wonderful meeting today. And I think I would stop here. Otherwise, I will keep on talking and then
Thank
then
you very much.
Kale would stop me then. Okay.
Thank you, Dr. Kale, Professor Kale. Thank you very much.
Thank you, sir. I would like to inform you that we have a international conference on multifunctional materials because we
Very
have
good.
foundation on 8th March, 8th to
Yes,
10th.
let it
So
in mind.
there we have called Dr. Rodney Rock, who is actually working on the graphene, and
Yeah.
magazine inventor,
Yes.
Professor Yuri, also is there
Very
on
good.
9th. So I
Very
would
good.
like
Very
to
good.
invite you. I would like to
Okay.
invite you at least on 9th, so that
Ninth. Okay.
8th and 9th, so that you can
Right.
participate, and
And
also
but will you
I
send
would
me
like.
the link?
Yeah.
Will you send me
Yes,
the
I have. Yes, I have sent you the link. But I want to on the brainstorming also, and at the end of the day on the 10th.
Very,
So
very good. Very good.
that's why I'm sending
Thank
you
you very
both.
much. Thank you very.
Thank you, sir.
Thank you very
Thanks.
much. Thank you.
Thanks
Thank
for
you.
your wonderful lecture, sir. Thank you very much. Sir, 1 minute, we would like to have one photograph. Okay, sir. Thank you very much, sir.
Okay,
Thank
thank you,
you.
Professor
Thank you.
Srivastava, and
Thank you.
thank you, Professor Sulba Kulkarni, being my teacher and saying good words about me. Thank you very much.
Thank
Thank you,
you.
sir.
Thank you.